Simple variables in programming languages typically designate a place in memory where data is stored.
For example, in the C statement, I equals j plus 1, the variable j on the right-hand side of the assignment designates retrieving a value.
Therefore, when evaluating a variable, as in the sample code shown, the symbol j evaluates to 3.
However, the variable in the left-hand side is the address or location of I, and with the assignment, a position in memory is updated.
Sometimes the behavior of a program needs many copies of variables of the same type, such as a string where each position holds a character.
Such organization of data is called an array, and an array has some interesting properties when the elements are placed consecutively in memory.
In particular, the time required to retrieve an element does not depend on which element.
Consider an array with 1,000 elements, for example, holding integers.
In C, this is declared using square brackets.
Moreover, the first element in the array is retrieved in an expression that uses the index 0.
In our running example, this is A of 0.
The 10th element in the array A is retrieved with A of 9.
In an assignment, such as I equals A of 100, or in an assignment such as I equals A of 234, the required fundamental operations to retrieve the item in the array are the same.
Although, we will see that the compiled code to retrieve an item in an array, given an index, are more than one.
That is, no matter the value of the index, recuperating the item in the array takes fundamentally the same effort, thus we can assume it consumes constant time. The time to execute the retrieval does not grow if we change the value of the index.
The same happens with storing a value into an array. No matter what position in the array we store the value, the same computation time is required.
Because of these properties of an array, arrays are referred as data structures with constant random access time.
In reality, access to items of an array in C, and most programming languages, are implemented by the support for arrays of the corresponding machine language.
Commonly, the ISA of a machine language offers some support to manipulate arrays, and we will illustrate such support here with MIPS.
However, when we work in assembly language, the size of the items in the array plays a role in calculating the address to retrieve data from memory, or store data to memory.
In MIPS, if we are representing an array of bytes, such as that of a string, then the cells, for each item of the array, are in contiguous addresses.
Finding the item at the first position is just the address of the array, but for the item at the second position, we need to move up 1 byte.
We now see why in C the first item has index 0, the address of the array and the first item coincide.
However, if we have an array of integers, each requiring 1 word, that is 4 bytes, then to find the address of the second item in the array we need to increment the base address of the array by 4.
In general, to locate item at position I, we need to multiply the size of the type of the array with I, and add this to the base address of the array.
In a programming language like C, the calculation of the address is abstracted from the programmer.
For example, the following code adds all the values in an array, and whether the array holds integers or shorts. The for loop iterates one by one.
However, in assembler, the size of each member of the array plays a role, and the equivalent code in MIPS must increment the register that is used to track the offset of the array by the size of the type, whether integer or short.